Good morning, Austin. So my name is Ross Kukulinski. I just started at Heptio. This is my third week at Heptio. Before that, I've been sort of an independent cloud-native consultant helping companies adopt and deploy Kubernetes. I've been doing that for about 2 years. I'm also heavily involved in the RethinkDB community. So I've been running RethinkDB in production for a couple of clients of mine over the last year or two. And so as the company sort of got shut down, I started getting involved on some of the community aspects and making sure that that project keeps going. I've been involved with the Node.js working group for evangelism. So it's a common thing I like to do, get out and talk to people and share ideas. And I've got an Introduction to CoreOS course from O'Reilly Media, and you can find me on the internet at Ross Kukulinski on Twitter and GitHub. So what are we going to talk about today? Well, we're going to talk about containers and storage and databases. First, we're going to talk about monitoring. We already talked about monitoring. That was a great talk. The motivation for containers. Why do we have these? Why do we care? And then we're going to dive into a brief introduction to Kubernetes 101. Then we'll talk about storage in Kubernetes. So how do you actually store data and persist information? We'll talk a little bit about operating databases, then some recommendations on which databases you should or should not run in Kubernetes. And then finally, we'll have a wrap-up. So without a doubt, containers really are having a massive impact in terms of the mindshare and technological innovation in businesses. We're seeing companies from not just Valley startups, but Fortune 100, Fortune 500 businesses leveraging containers in their production environments. And as a small sample, these logos are all from the Cloud Native Computing Foundation of companies that are running Kubernetes in production, which is pretty remarkable because Kubernetes is only celebrating its 3rd birthday in just a few weeks, and it's only been in production for about 2 years. So before we go any further, when I say container, what am I talking about? Well, in its simplest form, a container is a self-contained application manifest. It includes a file system, your application binary or binaries, their core dependencies, and nothing else. A container runtime, that means something like Docker, can launch your container on any Linux-based system, regardless of the underlying operating system. Now, if you've been in the industry long enough, you're probably thinking to yourself, these container things sound an awful lot like a virtual machine. Do we really need another virtual machine format? Well, containers really aren't virtual machines. So to be clear, these containers are not virtual machines. Now, the key differences between a container, which is on the left, and virtual machines on the right, are that the virtual machines have a complete guest operating system running in them. In addition, that guest operating system needs to have a hypervisor. That hypervisor is a translation layer. It provides this sort of abstraction so that your guest operating system doesn't need to know about the underlying host operating system. Containers don't have that. Containers, especially when I'm talking about containers, I'm mostly referring to Linux containers. Linux containers are able to leverage built-in systems in the Linux kernel that allow them to isolate processes. So this makes containers much more efficient and lightweight. Now, I do want to note that virtual machines do provide better process isolation compared to containers. So if you are running somebody else's code, or you're running in untrusted environments, you probably want to seriously consider staying in the virtual machine layer. However, there is a lot of work underway from security researchers that are looking to validate and mitigate the threat models in modern Linux containers, trying to make them as secure as virtual machines. In general, if you follow best practices and you're only running trusted code, containers are secure enough for most workloads. Okay, so what are containers? We covered what are containers. What do they buy us? Well, developers and operation teams are really excited about containers for really 3 key reasons: packaging, performance, and efficiency. So in terms of packaging, every container includes the application binary and their necessary libraries. Nothing else. And so this means that in the old days when you used to have a virtual machine that might run 3 or 4 different applications, maybe they have a shared conflict. Maybe they all require ImageMagick or some other library. And if you have one application that needs to have a newer version, you have a problem. You can't have 2 versions of ImageMagick installed in the same system. So containers provide a mechanism to eliminate that problem. Containers are also small. When built well, containers have sizes on the order of megabytes, not gigabytes like most of my virtual machines. And container images are immutable. So the artifact that you build in development, or maybe as part of your continuous integration, continuous deployment system, that image is the same. It's the same in QA, in staging, in production. And then if you have a developer that wants to figure out why the production container is having problems, they can download that exact image and run it locally on their machine. Performance. So if you have your own data center, because containers don't have that operating system layer and the hypervisor, your containers, the processes you have in your containers, they're going to have near bare metal performance. That's awesome. You're going to get so much bang for your buck out of your underlying systems. Even if you're not in a running in your own data center, because containers are able to start up so quickly, you can very easily dynamically scale your systems much faster. And you're not necessarily tied to the scalability of your cloud provider. So if you provision 10 virtual machines, you can scale your smaller applications, maybe your front-end application. You can scale it independently of your databases. And then that ties into efficiency. Because these the containers are small and lightweight, we can run a lot of them, and we can run them very efficiently on the same systems. So that all sounds great. Great, Ross, I want to run some containers. How do I do that? If you already have something, a configuration management tool like Ansible, Chef, or even good old Bash, they all have APIs and systems for you to launch and run containers in your infrastructure. The problem with these tools is that they're imperative. You, the developer, or you, the operations person, have to say, okay, run this container, and then when it's up, I want you to mount this volume, and then when that's up, I want you to start up this other container, and when that's running, I want you to connect it to the first one. If one of those actions fails, for example, there's not enough resources to launch that second process, then your whole script bails, and then you get paged. And getting paged is not fun. Container orchestration systems like Kubernetes or Mesos, however, approach this problem in a slightly different way. They come at it from a declarative syntax. As a developer, as an ops person, you define the desired state that you want. And those controls, the control loops that are running in Kubernetes, will continuously monitor the current state and continue to make changes to get to that desired state. And it's true that maybe that application fails, that new container fails to come up because there still aren't resources. But there can be another component in Kubernetes that realizes, oh, I don't have enough resources. I need to talk to my cloud provider, get a new virtual machine, and when that new virtual machine is up, that container will then be scheduled and run on that node. And so the real power from these container orchestration engines is that they're a platform that allows us to run our applications in this dynamic environment and think about how our distributed systems are running and scaling. And we can think at them from a higher level, a new abstraction level. Okay. So that's why we have containers. Let's dive into Kubernetes. So containers are not new. This is not a new novel idea. We had BSD jails, and if you were around in the 80s, we had chroot. You could have file system-based isolation of processes. Now, Google's been running containers for about 15 years in production. So when you access Gmail or search or ads, all of that are running in containers. They've got their own container infrastructure. And so as Docker was gaining traction, there's 3 people at Google, Joe, Beta, who Charity mentioned earlier, Craig, and Brendan. And they wanted to recreate Borg. Borg is Google's container orchestration engine. It's a proprietary engine. And they wanted to build a new one that was open source and give it to the community and build it in the open. And they really wanted it as an opportunity to drive more traffic to Google Cloud. And Kubernetes was developed with a strong focus on the experience of developers writing applications to run in that cluster. That's the intent. How can we build a system that makes it easy for developers to manage their own production infrastructure? And so Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. Now, because Google wanted to make sure that it wasn't just them, they donated Kubernetes to the Cloud Native Foundation, or Cloud Native Computing Foundation, which is technically part of the Linux Foundation. And now, a couple of years later, other key contributors to this include my employer, Heptio, but then big names like IBM, Microsoft, Red Hat, CoreOS, and 72 other companies. And so this community is more than just Kubernetes now. So Charity mentioned Open Tracing is another subsystem. FluentD is another project. There's a number of sub-projects now under the CNCF. So Kubernetes is just one of those. So Kubernetes, what do you say you do here? So Kubernetes is a platform, there's that word again, a platform, that abstracts away the messy details of running applications in the cloud as well as on-prem. And this higher level abstraction layer enables two key things. Number one is portability. If you run Kubernetes, your applications and the configuration you have that describes the applications in your systems that are running, you can run them on Google's cloud, Microsoft's clouds, Amazon cloud, OpenStack, your own bare metal infrastructure. And this is really, really powerful. The other key piece is extensibility. We have the ability to build on the Kubernetes primitives to create even higher level abstractions that allow us to think about and solve more complex problems. And we'll get to that more later on. All right, so let's talk about high level Kubernetes. So on the top left, we have a bunch of users. This might be you hacking away at a command line. You might be interacting with the system with an API or the CLI or maybe using a dashboard. And you're talking to the Kubernetes master or masters. This is really the brains of Kubernetes. And there's really three key components in the master, but we'll just talk about two. Number one is the API. So everything in Kubernetes is an API. Number two is the scheduler. So Kubernetes has a scheduler that understands the infrastructure resources that are available to the cluster and can provision things and place them throughout. And then we have our nodes on the bottom. Those are the worker machines that are going to run our infrastructure, run our code. And we can sort of abstract away the internals of the master, and we'll just have a nice little Kubernetes logo. So what does it look like when we want to deploy an application? So I've got a Node.js application, my app v1, and I can ask Kubernetes, hey, Kubernetes, I would like to run 2 instances of my Node application, call them my app, and I want 2 instances of the version 1. Kubernetes will look at the machines, the nodes that it has available, realizes they're completely empty, so it starts 2 instances of my app, dynamically spreading them out across the two different systems. Cool. That was easy. What if I want to update my application? Well, so I'm going to go ahead and change my application manifest that tells Kubernetes, I actually want you to run version 2. And so what Kubernetes will do is it will go ahead and start doing a rolling update. It will launch a new instance of my version 2 application on a 3rd node. Once that's up and running, it'll kill one of the instances of the old version, start another one, delete the 3rd one. So Kubernetes, as part of the core primitives, as part of the scheduler, has the ability to do rolling updates and blue-green deploys and really complex things that, having written some of these things in things like Ansible or Chef and Puppet, this I can write in 3 or 4 lines of YAML or JSON, whereas where I had to do it with Ansible was pretty long playbooks. Okay, so let's talk about disaster. Oh no! My machine went down. What happens? Well, Kubernetes looks and realizes that it has lost communication with that node. And so after a period of time, which depends on how you set up the system, Kubernetes will say, all right, that node is not in service. I need to spin up a new instance. And so it will go ahead up and spin another instance of my v2 of my application. So the problem is fixed. Now this wraps up our introduction to Kubernetes. This is real high-level stuff. The SYS platform does a heck of a lot more than this, but this is enough for us to build on for when we want to talk about storage, because we are at a storage and data conference. Data is a persistent problem. It's one thing for a developer to Dockerize their application and ship it to Kubernetes. It's actually pretty simple. It's a whole other problem, and arguably a whole different skill set to operate databases. Where do you put your data? How does your database scale? How do you do backups? And more importantly, restores? What happens if your database node fails? Do you need to worry about auditing? So one of the first questions when I'm working with a client or working with a company that's looking at Kubernetes and they're trying to figure out how to run their systems, and there I say, hey, I want to run my database in Kubernetes. I say, okay, do you have anyone on your staff that has operational experience with that database? If the answer is no, don't run the database at all. Pay somebody else to run it. Look to leverage database as a service, or look to your cloud provider to see if they have a solution for you. Or hire someone who does. Now, before transitioning to the world of containers in 2013, I was happily managing deployments of MongoDB and Redis using Ansible. Since that time, because I've worked with so many different companies, so many different sort of installations, I have run all of these databases and persistent systems on top of Kubernetes for production workloads, depending on how you define production workloads. It was production for my customers. So now let's talk about how we can manage the persistent state for these applications on top of Kubernetes. Now I'm a big fan of RethinkDB, so we'll keep rolling with the RethinkDB logo. So here I want to run a version of RethinkDB. I have a tell Kubernetes. I would like to run one instance of RethinkDB. Poof, there it is. Now, there's not hooked up to any storage. So if this container dies, or that node gets restarted, any data I might have there, it's gone. But Kubernetes has an idea of local storage. So we can map any application container that's running in our Kubernetes cluster. We can map to volumes that are on that underlying host. Depending on how you configured your systems, this is probably the highest performance option you have. If you have raw SSDs on a bare metal machine, your RethinkDB instance is going to have near native performance in terms of read writes to that underlying storage system. So what happens if you update what happens if you want to update to a new version of RethinkDB? What happens? Well, it's possible that our pod might show up on another machine. That's bad, because our data's there. There are some capabilities. Kubernetes allows us to lock specific containers to specific hosts. So that's one way to solve that. But that's sort of a Band-Aid, because what happens if our node dies? Our pod has to go somewhere else, but our data is on that original node. So we have to be really careful if we're going to run with a local storage paradigm. We have to be very careful about where our data goes. And there are some advanced systems and advanced tooling and advanced APIs that you can sort of craft your own solution to help mitigate against this. It won't be perfect, because that node can disappear at any time. And so this is a non-trivial investment. So if you need raw performance, this is probably where you need to go, but realize it's going to be expensive in terms of building the tools and the systems to make this a safe system. But Kubernetes is built for the cloud. So we can leverage external storage. All of your major cloud providers have their own remote storage devices. Basically, plug in like remote thumb drives. And so no matter where your pod is scheduled on any of these nodes, Kubernetes will talk to your cloud provider APIs and dynamically unplug and replug that remote storage device into the underlying host, and then connect it to your container. If you're running in your own data center or you're using OpenStack, you can use network-attached storage systems like NFS as other ways to run inside your system. Now, in general, this infrastructure, this paradigm, will provide the highest availability of your data. All the cloud providers have multiple redundancies, and they've got triple and quadruple nines to protect your data. But there is a performance trade-off. So your raw read and write and IOPS performance here is probably going to be a heck of a lot less than the local SSDs. So that's something to keep in mind. The other thing to remember is that your cloud providers usually don't allow you to move persistent disks from one availability zone to another one. So if you have a Kubernetes cluster that's spread across multiple AZs, your database instances may not be able to move across. So that's something to be aware of. Now, there's another really interesting paradigm that's happening is, well, we've got this cluster, and we have access to raw disks, and we have open source projects like Ceph and Gluster. Why don't we run storage in our own cluster? Can we get the best of both worlds? You can. So you can get excellent performance and high availability, but managing and operating Ceph and Gluster are non-trivial. So if you don't have people on your team that know how to do this and manage distributed file stores, don't do this. Now, I should note that there is a new open source project out. There's a company called Rook that's creating sort of an automated system to deploy Ceph on top of your Kubernetes cluster. It is very alpha. Be careful. Be very careful. But I think this is something that we're going to continue to see over the next 6 months to a year as file storage systems start to catch up and start to think about new ways to store data in the cloud. All right. We're a database conference. Let's talk about operating databases. It turns out this is really hard. Who here runs data, like who manages database instances in production right now? Like raise your hand, you're responsible for a database or two. Yeah. 1,000. That's a lot of databases. So you're probably aware that managing stateful applications like databases, caches, and monitoring systems, although maybe we're not supposed to be using monitoring systems anymore, it can be a big challenge, especially as you increase in scale. Each of these systems require some form of human operational knowledge to correctly scale, upgrade, and reconfigure these systems, all the while making sure that we're protecting against data loss and unavailability. Now, Kubernetes provides a number of primitives that can help with this. So these are things like stateful sets that allow us to be able to keep track of our different instances of our database. And we have things like init containers that allow us to do pre-initialization for container to move data around. Or we have jobs that we can run to do backups and restores. But the reality is that these are all primitives. These are abstraction layers, the primitives that allow us to build those things, but they don't all exist for all the databases that you want to use. So if you're looking at trying to run a database on Kubernetes, it's likely that you will need to adopt either open source scripts or roll your own that are customized for your particular data problems. That stinks. And so the folks at CoreOS have put out a new idea called a Kubernetes operator. And this ties into the fact that Kubernetes is a platform with extensibility. We have these abstraction primitives that allows us to build more complex systems on top of the existing system. And so an operator is an application-specific controller that extends the Kubernetes API to create, configure, and manage instances of your complex systems, or your databases. And they'll do it on behalf of you, the Kubernetes user. These all build on top of the Kubernetes resources and controller concepts. So the idea of being able to observe what is currently running in the system, analyze the differences between what the system has and where it's supposed to be, make changes incrementally, and then observe again. This sort of observe, analyze, act loop allows us to build systems that scale. This is exactly what Kubernetes does underneath the hood. But now instead of scaling containers or scaling your applications, we can apply this to databases, which is exactly what they did. So CoreOS built operators for etcd, which is their distributed key value store. That's also part of the Cloud Native Computing Foundation. And they also built one for Prometheus, which is a distributed monitoring agent. And the community has sort of jumped on board with this. There is an Elasticsearch one that was built out of, I think the University of Pittsburgh Medical Center built an Elasticsearch operator. I know that there's some work being done on a Postgres operator. If I had free time, I would build a RethinkDB operator, but I don't have as much free time. So really, these operators are probably the right way to start thinking about these abstractions. How do you want to run a database? You don't want to write a bunch of scripts that do this stuff. You probably want to write a system, or ideally have somebody else write a system for you. And so I think when we start looking at our database providers and our vendors, I'm hoping that they're going to start to recognize that this is an opportunity for them to stay relevant and make sure that they can keep their databases and grow the communities of their databases in this new cloud-native sort of dynamic environment. All right, so let's talk about some database options. So if you're evaluating Kubernetes as a potential platform for your company, what databases can you or should you run in Kubernetes? So let's go back to my slide of logos of databases I've run. I've added one new one, Cockroach Labs, CockroachDB. I have not run this yet. I'm starting to experiment with it, but I wanted to include it because I'm very excited about it. So, scale out or get out? At the end of the day, if your database is designed to scale up, not out, so Postgres and MySQL, I do not recommend running this in Kubernetes. Now, this doesn't mean that you shouldn't use those databases. By all means, do. They are great at what they do. Just don't run them in Kubernetes. Alternatively, you can leverage database as a service. You can use your cloud provider's database instances. Or if you're an organization that already has a database team, they're professionals at running these databases, and they already have systems for doing that. Say, hey, I just need an automated system to give me new databases on demand. They'll probably look at you funny, and then you can go back to these slides and explain why this is going to allow your organization to scale better and faster. If your database has some form of sort of primary, secondary responsibility, where there's the master that's responsible for all writes, and then you have read replicas that can become the master, these you can run in Kubernetes, but you have to be very careful because that master-slave transition is messy. And the tooling and systems, there is no Redis operator. So I have run Redis with Sentinel in Kubernetes. It's messy. It's not great. So you will likely have to build your own systems and your own tooling to sort of help with that automated failover. And it can be fraught with peril. Finally, cloud native for the win. If your database has built-in systems for things like peer discovery, sharding, replication, and probably most important, automated failover, congratulations. These systems have all been built with node and instance failure in mind, which means that they will work and run exceptionally well within Kubernetes. But remember, there's a big gap between getting something to run in Kubernetes and making it production ready. This is especially true when we're talking about persistent storage systems. If you lose your data, you might be in big trouble, especially if you're in a company that's got auditing requirements. So make sure that it is in fact production ready before you run it. Kubernetes operators can help with this. So if your database happens to have an operator, jump on board, get involved with that, because it's probably the right long-term direction to run that database inside of Kubernetes. But in the short term, expect to build your own extensions for your specific use cases. Okay, wrap up. So in summary, leverage database as a service or your teams that do that for you. It's just going to be easier, especially if you're a developer without operational expertise in your databases. Container and orchestration systems like Kubernetes are really changing the way that we deploy and scale and think about our distributed systems. And they provide an extensible platform for us to build even more complex systems like distributed databases. And so Kubernetes can be a great place to run your cloud-native databases. I've been doing it for a number of them, but just be careful about which databases and how you build and scale out those databases. Thank you.